Hello and welcome back to another multivariable calculus 3 video. Today we are going to be talking about Lagrange multipliers. Let's just dive right into it. This is going to be a long one. What is a Lagrange multiplier? Well, it's essentially a method to find a maximum and minimums, right? So we talked about maximums and minimums in the last problem, or in the last video, but this is just another way to talk about it. I'm going to get more into the why after this picture here, but say we're given some kind of function. Think of it like almost like a domain, you could think of it as, and another function in which we are trying to find the maximum of our other function inside of that function. I have this picture here, so we're going to start using the diction here. Say we have some kind of constraint of our g of xy, and then we have our z is equal to f of xy function. Well, we can essentially find the maximum of that f of xy. That's essentially what a Lagrange multiplier is. So I guess let's kind of just look at the why here. Why we're doing this is to maximize and minimize based on a constraint. Our constraint being our g of xy, well, we're trying to find the maximum of our blue function inside of the red function, and I kind of drew a photo there where that occurs, but how are we going to go ahead and find that? Well, let's get into the how now. How is going to be, we're going to be using this neat little formula here. Well, we're going to be taking the gradient of f, and we're going to set that equal to lambda times the gradient of g. This is what a Lagrange multiplier is. That's just the formula for it. So how are we going to solve this? How are we going to find our extrema? Well, what we're going to do is, like I said in the last video, I love my 3-step processes. We're going to set our gradient of f equal to lambda times the gradient of g. We're going to make a system of equations from that. I will get more into how we're going to do that within the example, because quite frankly, Lagrange multipliers is something that, if you just do examples, you're going to get it. It's not really something that's too intuitive, at least it wasn't for me. We're going to solve our system of equations that we create from our original equation, del f is equal to lambda del g. We can solve our system for lambda in the right case. I will talk about when that can happen and what you need to be careful for. Or you could also solve it for cases. Also something that I will get more into. And finally, we're going to test and classify our points for extrema. So I guess we need to understand some diction here, because this is really going to be, we have two pieces within the Lagrange multiplier. We have our objective function and we have a constraint function. Well, what is our constraint function? Our constraint function is that little red function right there. It's going to be where we're trying to find our objective function in the blue, the maximum of the objective function inside of the constraint function, is the best way I can try to explain it here. That's going to be the diction that you're going to hear for Lagrange multipliers. Is we have an objective function and we have a constraint function. So let's just go ahead and dive into an example. The best way to learn these is to do examples. So we're thinking we're going to do 2 today. This one should be pretty simple. Let's go ahead and get started. We're given f of xy is equal to x times y, subject to x squared over 8 plus y squared over 2 is equal to 1. Find the maximum and the slash minimum. And then in my little pink there, this is going to be a problem we're going to solve for lambda. Going to get more into that right now. Well, let's go ahead and use our handy-dandy formula. Del f is equal to lambda del g. Well, what is this? We're going to take the gradient of f, and we're going to take the gradient of g. Well, what's the gradient of f? What's the partial of this function with respect to x? Well, that's just going to be y. Inversely, what's the partial of our function, our objective function? I'm going to try to use the addition that I just taught you to make sure it doesn't seem like I just said it for no reason. Of our objective function, what is our partial for y? Well, that's going to be x. And then coming over to our constraint function, well, what is our partial for our constraint function? we're going to go ahead and make it, what is it? We're going to have g of xy is equal to x squared. G of xy is equal to x squared over 8 plus y squared over 2 minus 1. What's the partial there? Well, power rule, 2x over 8, that's going to be x over 4, right? Going to be our first part. And then same thing over here for our partial in terms of y of our constraint function. We're going to have 2y over 2. That's just going to be y. So we have everything we need to get this bad boy going. So let's just go ahead and set them equal to each other. We have gradient of f, which is yx, equal to lambda times our gradient of g, x over 4y. So let's go ahead and make our system of equations here. Well, what are we exactly doing? Well, we're setting our x values equal to each other, and we're going to set our y values equal to each other as well. So let's just go ahead and do that. I color-coded it there, maybe not the best idea, but we have y is equal to, can't forget this lambda, we'll do that one in yellow. Lambda x over 4. That's our first system. Our second system is going to be x is equal to my pencil died here. Hold on. Not working. There we go. X is equal to lambda in our yellow, y. And then, well, we have a third one that we're going to use here. This is kind of essential when doing Lagrange multipliers. We need an extra system to account for our constraint. Well, what's our constraint? Our constraint is x squared over 8 plus y squared over 2 minus 1 is equal to 0. We have three systems of equations, and we have our total system of equations. So what are we going to do here? Well, we're going to solve for lambda. That's going to be step number 2 here. We're going to solve our system for lambda. Well, how are we going to do this? Well, we have two of our systems of equations here. There's no lambda in our third, our constraint, so we can't really do that. So let's go ahead and solve for lambda in our first system. Well, how are we going to do that? We're just going to multiply, or we're going to see, what are we going to do here? We're going to multiply by 4, divide by x. So we're going to have y times 4 over x is equal to lambda, which is going to equal to 4y over x. Well, there's something that we really need to be careful here whenever we do this. What happens when we divide by x? Well, we're allowing for there to be a possibility that we divide by 0, and that's going to make our system of equations invalid. Therefore, we need to make sure that this x value cannot equal 0. So let's just make we're going to make a big red note of that. Division is risky. That's why solving for lambda is oftentimes risky. It's simpler than doing cases, but it's certainly risky. So how are we going to make sure that this x is not equal to 0? Well, let's just go ahead and think about it. In our second system of equations, we can just prove that x is not equal to 0 there. Well, if our x is equal to 0, then that means our y is also equal to 0, meaning what? Well, if we plug in x is equal to 0 and y is equal to 0 into our constraint, well, we're just going to have 0 is equal to negative 1 there, meaning our x cannot equal 0, therefore our y cannot equal 0, therefore neither of them equal 0 because of that constraint. So it's safe in this scenario, but that's just something you always want to look out for whenever you're you're dividing by variables, because that's a very risky move and it can very well set you back and give you the incorrect answer. So now that we've established that doing this is pretty safe, we can go ahead and just solve for lambda here as well. We have lambda is equal to x over y, just divide that y out. in our second system of equations. So we have two lambdas. Well, let's just go ahead and set them equal to each other. That's how we're going to solve our system of equations. So we have 4y over x is equal to lambda, which is also equal to x over y. These lambdas are the exact same for each system of equations. So we have this. We have 4y over x is equal to x over y. Well, let's just go ahead and multiply this out. We're going to have, what, 4y squared is equal to x squared. Take the square root of both sides. Actually, reminisce to do that because, let's move this down here. Well, what we're going to be doing is we're going to be solving our system here, and in order to solve our system, we need to find our x and y. Well, in our constraint here, we could easily just plug in this into our constraint, right? So we have our x squared, we solved for the x squared, and we solved for the y squared. Well, we could plug in either or into our constraint function, and that would give us whatever variable we choose is equal to, and inversely, we can just go ahead and plug whatever we solve for into our 4y squared is equal to x squared, and that'll give us what we're looking for. Perhaps poorly explained, but I'm just going to go ahead and do it. Well, plug into our third system equation. We have 0 is equal to x squared over 8 plus y squared minus 1. We're not going to solve for y squared in here. We're just going to go ahead and plug in that x squared. So we have 0 is equal to 4y squared over 8 plus y squared minus 1. That's just going to be 0 is equal to 1/2 y squared plus y squared minus 1. We have 1 is equal to 3/2 y squared, meaning we have 2/3 is equal to y squared. Let's see here. 2/3 is equal to y squared. Did I make a mistake in here? X squared, y squared, 4y squared over 8. 1/2 y squared plus y squared minus 1. We can actually just go ahead. Never mind. I did a little bit too much work there. I got a little bit too big for my britches. That was not necessary. Well, that's going to be... Oh, I plugged in the wrong equation here. Sorry. It's y squared over 2. I knew something was wrong there. Yeah. Okay, now we have 1/2 y squared plus 1/2 y squared minus 1. So then we have 1 is equal to y squared. I apologize. Take square root of both sides. Our y is going to equal positive or negative 1. Should be right. I knew something was off there. I failed to look at the original constraint. I apologize. So we have y is equal to positive or negative 1. Just plugging that in over here, if y is equal to positive or negative 1, it really doesn't matter. Our x is going to be the same thing. If we take the square of positive or negative 1, it's just going to be 1. Therefore, our x squared is going to equal 4, meaning our x is just going to equal to positive or negative 2. Let's show our work. So we have 4 times 1 squared is equal to x squared. That's going to be 4 is equal to x squared. X is equal to positive or negative 2. So therefore, we have y is equal to positive or negative 1 and x is equal to positive or negative 2. Those are our critical points on the constraint of our function. Well, let's just go ahead and make a neat little thing here. We have, if y is equal to negative 1, well, there's two other scenarios. X is equal to 2, or x is equal to negative 2. And if our y is negative 1, well, we have x is equal to 2 as well, or x is equal to negative 2. So therefore, we have, what is that going to be? 1, 2, 3, 4. We're going to have 4 critical points here. So our critical points are going to be, well, what is this? Y. That is going to be 2, 1, and negative 2, 1. So we're going to have 2, 1, negative 2, 1. And then coming over here, we're going to have 2, negative 1, negative 2, negative 1. So we're going to have 2, negative 1, negative 2, negative 1. Those are our 4 critical points that we solve for using Lagrange multipliers. Well, how are we going to test what is a maximum and a minimum? Well, we have our critical points here. We're just going to go ahead and make a table out of this. Why not? How are we going to test what is a maximum or a minimum? Well, you could think about this harder than you may have to, but we just kind of know that what's a maximum, it's when our value of our function is the greatest it can be. What is our minimum? When it's the least it is that it can be within our given critical points. So we're just going to go ahead and test our original function with these critical points. Well, what is our original function? That's going to equal xy. So just plugging in our critical points here, we have 2 times 1, that's going to equal 2. Negative 2 times 1, that's going to be negative 2. 2 times negative 1, negative 2. Negative 2 times negative 1, that's going to be 2. Therefore, we have 2 critical points here. We have a maximums, I suppose, at 2, 1 and negative 2, negative 1. And we have minimums at negative 2, 1 and 2, negative 1. That is how we are going to find our maximums and minimums, solving for lambda within these Lagrange multipliers. Let's go ahead and do another example here where we're solving for cases in this one. I might have to actually make another page for this one. We're solving for cases for this one. Let's go ahead and just do our process here. We have gradient of f is equal to lambda gradient of g, our Lagrange equation. Notice that this is in 3 variables here. Not too difficult, not too different, I suppose we could say. Well, what are we asked to do here? I guess maybe perhaps I didn't write that down. We're going to find distance closest to the origin. Okay, now we're ready to get going here. Well, what's our distance equation? Well, we might understand that from prior calculus classes, our distance from some point is going to be the square root of x minus a squared plus y minus b squared plus z minus c squared. That is our distance equation. Well, if we're trying to minimize this, that's essentially what this is asking, is minimize the distance to the origin. Well, the origin is 0, 0, 0. Therefore, our distance is going to equal the square root of x squared plus y squared plus z squared. Well, what does that mean? That means that this distance is the square root of that. Well, if we take the square of both sides, then we have our d squared is equal to x squared plus y squared plus z squared. And this is easier to work with, as we can see, and we can kind of understand why that this is the same thing as d is equal to the square root of x squared plus y squared plus z squared, and why d squared is the same thing as that. No matter what our x, y, and z are, the number is going to be the exact same thing, right? So I messed up, Haiti.